So, coming back to where we left, so we were looking at the two different definitions for stresses, the engineering stress, stress which is in general defined as force by area, and if you take the original area then what we get is engineering stress, and if you take instantaneous area then what we get is the true stress. And if we apply to this the fact that AI Li is equal to, because the volume remains constant during plastic deformation, we are talking about plastic deformation, and therefore AI Li is equal to, which is initial instantaneous volume is equal to the original volume. We can apply to this, and what we will get, it can be shown so again we have a relation, so which relates sigma engineering to sigma true. So you can calculate sigma engineering very easily, and from there you can obtain sigma true. One thing that we have to be careful is that these relations apply only up to the point where we get uniform deformation. We will talk more about uniform deformation in a material, but briefly let me describe what it is. So if you are doing a simple tensile test, if you remember, the plot looks something like this. So up to this point, up to the point where necking takes place, what we have, the plastic deformation starts somewhere over here. So from here all the way up to here, the deformation that you have is uniform, meaning the whole gauge length or whole area which is subjected to that deformation is deforming uniformly or has similar amount of deformation. Beyond this, what happens is that one particular region, in this case neck, where the neck has formed, that particular region starts to deform more than the other region, and therefore you cannot describe the area or the change in length to the whole material or the whole sample, and that is why these relations, this one and that for the true strain, cannot be valid beyond this point. So these are the simple definitions for stress and strain, but stress and strain are not so simple, and there can be stresses in multitude of directions. Stress is not a scalar quantity, it is a tensor quantity, not even a vector, it is a tensor quantity. So to get to that level, now let us look at some more intricacies about stress and strain. Let us say we have a material of this shape where it is pinned it is pinned at those two regions, and it is being deformed like this, or basically the force is being applied from here in this direction. Now each and every point will have the direction of stresses will be very different, and there will be not just one component there. If you try to resolve it in the different directions, there will be multitude of directions. So to understand or to resolve this, what we use is what is called as continuum mechanics, which is nothing but just simply saying that in order to understand stresses and strains, we are assuming that this body is continuous. That is, you are not looking at it as sum of atoms. At each and every point you assume that it is uniformly solid or with uniform properties, and then you describe what will be the stress and strain. So now let us say at one particular element over here, it is actually very small, but I am, for the sake of understanding, I will say that this is how it looks. Now let us take an element which can fill the whole space, and cube is a very nice such element. So we will take one cube over here and put it in larger view. Now this is one element, a very small, infinitesimally small element from here, and it may be having, or it may be getting exposed to different forces. Let us say one force in this direction and something like this. It will be very difficult to understand this, and therefore what is done is that you resolve it in 3 different directions and in 9 different components. So, here this will be sigma x, this will be called sigma xx, this will be called sigma xy, this will be called sigma xz. Similarly, here it will have 3 components, this will be called sigma zz, this will be called sigma zx, this will be called sigma zy, and similarly here it will have 3 components, sigma yx, sigma yz and sigma yy. Now, these 9 components describe the complete stress state at this particular point in the system. Now, similarly, there can be different variations or different values of these 9 components at different points, but once you describe it in these 9 components, you are able to see the complete picture at least at that particular point, and that is why it is described or easier to understand in this direction or in this particular fashion. Now, here couple of things that you should observe. One, that there are some what are called as normal stresses. So, you see these are acting normally to the surface of this element. Other stresses that you see over here are actually in the plane, and these are also called as shear stresses. So, we have 2 different, so we are in a position to say that there are 2 different kinds of stresses, normal stresses and shear stresses that act onto this. Another thing is that now we have these 9 elements, and since it is a tensor quantity, the sigma stress can actually be written like so. Now, this stress has 9 different components like this, and the components which we were calling as normal stresses are actually the diagonal component of this, and the stresses which we were calling as shear stresses are the non-diagonal elements. So, there is symmetry to this, all the stresses that are normal are coming in the diagonal and the shear stresses are the non-diagonal elements. And this sigma xy, which is also, which I said, as I said, is a shear stress, is also represented as tau. So, very often we will interchangeably use this notation, or we may also use something like this. So, I am putting it out here so that you do not get confused later on. We may interchangeably use the notation tau xy or sigma xy, and when we use this one we can use sigma xx or even sigma xx, sigma x or sigma xx, that does not matter. But the thing is that these are the shear stresses are many a places represented as tau. Now, this is the 3-dimensional version of it. You can also have a 2-dimensional version of it. So, let us say their stresses were all in one plane. In that case, we would be representing it as, why we are looking at 2D is because many a times in most of this deformation you would see that we are able in a position to simplify the model or simplify the condition to a plane stress condition, or in some cases plane strain condition, and therefore, we are able to get we can get rid of many of these elements and make our life easier. So, let us say these are the x and y direction. So, this is sigma x, this is sigma y, and of course, there are shear components. So, this is tau x, tau yx, which is also here tau yx, and this is tau xy, and this is also tau xy. Now, can you say something about tau yx and tau xy? In general, can we say anything about this? If a material is in equilibrium after deformation, can we say, or even if it is not getting deformed, but it is being under the under some imposed stresses tau xy and tau yx, can we say something about tau xy and tau yx? Yes, we can, and we can say that it has to be tau xy has to be equal to tau yx. Why? Because let us say it is not equal, tau yx is greater than tau yx is greater than tau xy, then it will start to rotate. But we know that our body is in equilibrium, and therefore, these two elements must be equal, and therefore, in all these we will always have tau xy equal to tau yx, and that also means that our matrix has been reduced to sigma x, sigma y, tau xy, and this is also tau xy. So, in effect we have only 3 elements, and the same way we can also talk about tau xy sigma xy equal to sigma yx, and therefore, all the 3 elements that you see over here will be equal to the 3 elements over here. So, even in 3 dimension we do not have actually 9 independent terms, we only have 7 independent terms, sorry 6, 3 plus 3 6 independent terms. The other 3 are equal to this other 3, and therefore, in 3 dimension we have 6 independent terms, and in 2 dimension we have 3 independent terms that we need to find out or we need to look at. Now, that we have looked at the stresses, the next thing that we can look at is a simple application of these stresses in a particular condition. So, let me draw a simple configuration to explain how the same element, if you look in different direction, can have different values of stresses. So, let us say this is the white one that I have drawn is element onto which we intend to measure stresses, and this is some weight that has been put onto it. Let us say W is the total force, not just the weight, but weight times gravity. So, this is the total force that is acting onto this element. So, if we were to look at this particular area, which let us say is equal to A, the cross sectional area of this element or this bar that we have over here, if we were to look at this, then the sigma for this will be equal to W by A. Throughout anywhere, if you look at any cross section, the stress in that cross section would be equal to W by A. So, that is our, let us call it sigma naught. But now, let us say we are interested in a plane which is oriented a little differently. So, let us say we are interested in finding the stresses on a plane which is oriented like this, which is phi, at an angle phi to what we have. So, it is inside the same material, but we are now interested in measuring it in a different orientation. You can call it change of reference frame, or you can call it a different point of view, different measuring it from a different direction. So, but whatever it is, we are interested in measuring the stresses over here. So, now let us draw this element over here separately, and so this is now here the force that is acting onto this is actually total force is like this. and it is not normal to the surface. So, what do we need to do? We need to resolve it in Fn normal and Ft tangential. So, you see initially we had only normal component of the stress, and because now we are measuring it in a different plane, we have inadvertently added a shear stress component to it. So, there was only normal stress, and now we have normal plus shear stress, and this angle would be what? This will be phi. Now, you can see that Fn is equal to W cos phi, Ft is equal to W sin phi. Area over here, this area is also now changed. So, if we were to talk about this A prime, let us say, then this is equal to A by, or let us call it A phi. So, A phi is equal to A by cos phi. So, now if I want to find sigma yy, which is in this direction, and in this direction it will be sigma xy, because it is a shear stress. So, if I want to find sigma yy, which is normal stress, it will be equal to Fn by A phi. And we said we have given a value of sigma naught to W by A. So, it becomes sigma naught by cos square phi. Similarly, for sigma xy, which is now the shear stress, there is Ft by A phi, which is equal to W by A is equal to sigma naught So, there are a couple of things to note here. We started with a condition where the force was normal. So, this rectangular bar had only normal force acting onto it, but depending on a configuration or the situation, you may have to look at forces in a different direction and then resolve it. So, in that different direction, which happens to be this at an angle phi, we see that here the forces are not normal anymore, just it does not have only the normal component, it also has a tangential, which means now there are normal stresses as well as shear stresses. Another thing we note is that there is a relation between the normal stresses and the original stress that was acting. So, there is a way to transform axis or transform the reference frame, that is another thing that we understand from here. Similarly, you can also get the shear stress component from this original sigma naught. So, we can transform and get not only the normal stresses, but we can also get the shear stresses. So, both normal stresses and shear stresses can be transformed, can be obtained by transforming from the original normal stresses. That is one thing. Now, let us put some values and see something very strange over here. Okay. Now, let us say that I put phi equal to 90 degrees. What does that mean? It means that phi is right now here, now it becomes like this, and we are still looking at normal, that is normal in this direction, and shear stresses like that. But what is the value that we get? If you put phi equal to 90, we know that it is 0. So, sigma yy becomes 0. If we put fxy in over here, again we put phi equal to 90, then again this becomes 0, and therefore sigma xy is equal to 0. Now, suddenly we see that although stresses are being applied, but both normal stresses and shear stresses in this particular plane have reduced to 0. So, that sounds little strange, but it is not really that strange. We will be able to explain it in a few minutes when we look at the explanation using Mohr's circle. You must remember Mohr's circle from your undergraduate days, but if not, do not worry, we will look at just the basics of these in the Mohr circle. But before that, You can again put another value which is phi equal to 0 degrees, that is just like this, which is same as that. And what do we see, that sigma yy, if you put phi equal to 0 it becomes 1, and sigma yy is equal to sigma naught, and sigma xy, if you put phi equal to 0 in this, it is again 0 and this is again 0. So, we get the original solution back when we put phi equal to 0, that is only normal stresses acting on over this. So, this particular example has helped us understand couple of things, that depending on the orientation of the element, even if it is at the same point, see, remember whenever we talk about element inside the component, and our component is this rectangular bar, inside it we may be looking at a very small component over here, a very just like a point. So, in that point, if you were looking at the stresses in this direction, then it was just normal. If you just took this element and rotated it by phi, you get not only normal but also shear stresses with a little different value, and also up to in a particular condition you see that there is normal stress is also 0 and shear stresses are also 0. So, these are just elements and you rotate them. So, the same stress state can be expressed in quite a bit different ways, that is what we are trying to express over here. And when we talk about this example again, which is phi equal to 90 degree, what we will talk about is mainly that there are principal stresses, and that not both the principal stresses have actually reduced to 0. So, this is a principal stress and this is a shear stress, but there is another principal stress component. We will define all those things, but I want to give you the answer beforehand, and that second principal stress is not really reduced to 0, that is still does exist over there. Okay, so, coming to understanding the stresses or the Mohr circle a little bit more, let me talk about these elements, just a little bit more about these elements. Now, you saw that we started with a single element where there was no shear stress, but when you rotate it, meaning at the same particular point, even though we are at the same particular point, we were able to get, but just by rotating or in looking at it in a different direction, we were getting shear stresses. So, we can start with just normal stresses and transform to normal plus shear. Values may be different, but the idea is that shear stress does not arise, basically shear stress is not an completely independent quantity that will, that when you only apply shear stresses will be generated. Even when you apply normal stresses, shear stresses are generated inside the material. So, we saw this, and inverse of this is true, meaning if you have normal plus shear, you can transform to only normal stress condition. So, even though we start with shear stresses along with normal stresses, but if you keep rotating, you will get to a region, and in fact, in every condition you have to get to you will always have a particular orientation where you will get just plain just the normal stresses, and that particular normal stress, this normal stress is called principal stresses. So, we talked about principal stresses earlier, without giving definition or understanding, but now I am explaining what is this principal stress. Again, I warn you that do not get intimidated by all these terms. These are just starting points where we are using some equations. Later on, when we get to the real examples, you would see that what we use are much simpler form of these equations. But since we are talking about fundamentals, it is important that you get to understand all these basic fundamentals. So, these are called the principal stresses. And why do we talk about principal stresses? Because principal stresses are important in determining yielding. You may remember from your high school and even from your undergraduate days that when you do a simple tensile test on a dog bone, there gets a region where what we call as yield point, and we say that beyond this plastic deformation takes place. So, in a simple uniaxial deformation, it is very easy to determine or define where the plastic deformation starts. But as you saw, we were looking at complex state of stress, where you have not only one component of stress, there can be as much as 6 different components of stress acting on different points. In that particular condition, how would you say that the material would yield? Would you say that sigma xx reaches this value, sigma xy reaches this value? Is that will not be so feasible if you try to define each and every individual element and say each of these should reach this value when yielding takes place. In fact, you would see that the hydrostatic stresses are not even related to yielding. So, you can easily get rid of 3 of these terms, and what you can look at, even in the most general case, the yielding would depend only on 3 different values of stresses. And that is why understanding the principal stresses becomes important. Where you can principal stresses, if you remember, are the stresses in the condition where you are not talking about shear stresses. So, either you talk about normal stresses and shear stresses, in which case you have 6 different components, or you talk only about principal stresses where you have then 3 components, and in those 3 components what will be the yielding. So, equations relating to the yielding of these in the next class. Thank you.